So at this point, we finish what I consider to be the kind of core topics of game theory, which is normal form and extensive form, up to games of imperfect information. So that takes us 4 weeks in. So at this point, we're going to start kind of jumping between topics a bit, which extend the basic concepts of game theory in various different ways. So the topic of this week is repeated games. So the idea of repeated games is that we take an existing game, which is typically a normal form game, and then we play it several times successively so that the players see what happened in previous runs of the game. So the game that we're going to repeat is called the stage game. So a repeated game consists of a stage game together with some kind of mechanism for repeating it. So in this video, we're going to be looking at finitely repeated games. And then for the rest of the week, we're going to be looking at infinitely repeated games, which are much more interesting, but also much more complicated. Okay, so in a finitely repeated game, typically we're going to say that the payoffs that result from playing a repeated game is going to be the total sum of the payoffs that we get from playing the stage game each of a bunch of times. So the idea is that we're going to play the stage game. So let's say we take Prisoner's Dilemma and play it, say, 5 times. In each round, we're going to have some combination of choices of cooperate and defect. And so in each round, the players are going to get payoffs. And then the total payoff that they're going to get is just going to be the sum of those. So typically, the players are going to have perfect knowledge, perfect information about what happened in all of the stages before the current one. So that is to say they can observe the history of the play up until the current round. But in the current round, they're usually going to have imperfect information. So that is to say, if we're repeating a normal form game, then the players are not going to know what each other are doing in the current round. So this is kind of obviously an interesting thing to do if we want to model real world situations, because most of the time in practice, interactions don't happen just a single time, but they happen repeatedly. So players can, for example, form reputations or opinions about what each other are likely to do. To a certain extent, we can draw pictures of repeated games. Of course, this gets quite impractical very quickly, but so this is just about the biggest one where I can draw it and you can have some idea what's going on. So this is a 2 times repeated Prisoner's Dilemma, drawn as an extensive form game. So here you say we have the first round, and in the first round, we have an information set which says that these moves are happening, player 1 and player 2 are really moving simultaneously. And then in the second round, so each of these branches here represents the second round after each of the possible plays of the first round. And the information sets are set up so that both players know exactly which play happened in the first round. So here, for example, player 1 knows exactly where they are, and player 2 doesn't know what player 1 did in the current round, but they know exactly that they're in this subtree, because these don't share information sets with any nodes over here. And then these payoffs are set up so that in each case, so we have, I think, cooperate is always the left branch and defect is always the right branch. And then I've set up the payoffs to be the sum of the individual Prisoner's Dilemma payoffs for the 2 rounds. Okay, now, because this is just an ordinary extensive form game, we can solve it by backward induction. So here, this is a kind of recap of what we were doing at the end of last week. In this tree, we have 4 minimal subgames, namely this, 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 and this. Now, if you think about it, each of these is basically a copy of Prisoner's Dilemma, except that we've shifted the payoffs. We've added a constant to the payoffs. So, for example, here, so this is the Prisoner's Dilemma we play after cooperate happened in the first round. What we've done here is we've taken Prisoner's Dilemma and we've added 2 to the payoffs of both players. So three. Three being the, no, it is two being the payoffs of cooperation. Now, if you remember, I told you once that Nash equilibria, or kind of almost everything in game theory, is unaffected by applying a positive affine function to the payoffs, which means that for every reasonable purpose, this thing here is just a prisoner's dilemma. In particular, this thing has a unique Nash equilibrium, which is still defect-defect. Adding a constant to all of the payoffs doesn't change that. So we have a unique equilibrium here in this subgame, which is defect-defect. And it's the same thing here. So in each of these cases, we've taken prisoner's dilemma and we've added constants to each of the players' payoffs. So it's a different constant for each of these subgames, but within each subgame, it is just a transformed copy of the prisoner's dilemma. So in every case, it turns out that we have a unique Nash equilibrium, which is in every case defect-defect. So what that means is that we can do backward induction. We can replace each of these four subgames with the payoff resulting from defect-defect. Now, if you then think about what happens next, so I've done that here, and now I had a bit more space to work with, so I've written these sums explicitly. So now kind of turn your brain inside out and think about this from the perspective of the first round. This is now also a copy of ordinary prisoner's dilemma, except that we've added a copy of the defect-defect payoff from round 2 onto every branch. So again, we get a unique Nash equilibrium, which is defect-defect. So what that means is that we can completely solve this game by backward induction, and we conclude that this game has a unique subgame perfect equilibrium, which is both players always defect no matter what. In particular, even if defecting didn't happen in the first round, so in these three subgames, something off equilibrium has happened in the first round. But even then, the subgame perfect thing to do is to go back to defecting. Okay, and I hope you can see that this kind of reasoning would work for any finite number of repetitions of prisoner's dilemma. So in theory, even if we played prisoner's dilemma 1,000,000 times, in theory, we are going to get still a unique subgame perfect equilibrium, namely all players defect, which is a bit strange when you think about it, because of course, if they cooperated, they could get very significantly higher payoffs. What's happening here is extremely similar to what happens in the centipede game. It's a kind of paradox of backward induction, that as long as you have a finite game with a determined endpoint, backward induction says that the players are going to kind of work backwards from the end and kind of eliminate things that won't be rational later. Okay, so the conclusion we reach is basically that finitely repeated games are boring. In general, if we have a finitely repeated game, a subgame perfect equilibrium of it is going to look like play some Nash equilibrium of the stage game in every stage. So what this essentially tells us is that finitely repeated games don't do any new tricks, where it's not a kind of significant extension of the theory of normal form games. It's just kind of more Nash equilibria. Now, as we're going to see for the rest of the week, this is heavily in contrast with what happens when we play a game infinitely often. So there's a big subtlety here, which is that the behavior of an infinitely repeated game is not like the limit of the behaviors of increasingly long finitely repeated games. We can play any finite number of repetitions of, say, the prisoner's dilemma, and we can make that longer and longer. But then when we jump to infinity, the behavior of this game is going to very fundamentally change. So in particular, if we have an infinitely iterated prisoner's dilemma, this is going to have subgame perfect equilibria in which there is cooperative play. So we're going to spend the rest of the week studying what this means.